Welcome to the class on quantum mechanics. Uh, Today we will discuss about Bohr's correspondence principle, Bohr's complementarity principle, wave packet, wave function, physical and probability interpretation of wave function, group velocity and phase velocity, and uncertainty principle. So first we discuss about Bohr's correspondence principle. Niels Bohr suggested that the quantum theory should reduce into classical theory when quantum effects are insignificant, which means that classical mechanics is an approximation of quantum mechanics, even though the classical mechanics originated first or developed first, after that quantum mechanics. We know that quantum mechanics developed around 19th century or 1905 or around that time, but we know that classical physics, which is well below that, so well above that, classical physics is well above that. Bohr correspondence principle states that quantum physics reduces into classical physics at a large quantum number. To explain this principle, Bohr used simple illustration based on the line spectra of one electron atom. Line spectra of one electron atom is nothing other than hydrogen itself. Okay, so to explain this principle, Bohr used a simple illustration based on line spectra of hydrogen atom. In the Bohr model of hydrogen atom, it is shown that the energy levels are proportional to 1 by n square. See, the energy levels are proportional to 1 by n square. You can imagine for n is equal to 1, okay, nothing happened. N is equal to 2, n is equal to 3, n is equal to 4. See, there is 1 by n square term. As the n increases, 1 by n square term also increases, which means that the energy levels are discrete. We already know about the spectrum of hydrogen atom. The energy levels are discrete, and for larger value of n, the energy levels are so close that it seems to be a continuous one. Okay, so in Bohr model of hydrogen atom, it is shown that the energy levels are proportional to 1 by n square. Energy levels are proportional to, or we can say En, E suffix n is proportional to 1 by n square time. And for larger value of n, the energy levels are so closely packed so that we can consider this one as a continuous one. Okay, so which means that in quantum mechanics, the energy levels are discrete. In classical mechanics, the energy levels are continuous. Once again, I would like to repeat. In classical physics, the energy levels are continuous. In quantum mechanics or quantum physics, the energy levels are discrete. For larger value of n, what happens is the energy levels are so close that it seems to be a continuous one. Okay, so Bohr correspondence principle, which states that quantum physics reduces to classical physics for larger value of quantum number. For example, n. Okay. Next is Bohr complementarity principle. Uh, the previous class we discussed about particle theory of light, which is photoelectric effect and Compton effect, which means that photoelectric effect demonstrates the particle nature of wave. Okay, so photoelectric effect or Compton effect that demonstrate the particle nature of wave. But uh, before that time, we know that light is a wave, because interference and diffraction, these type of phenomena could be explained with the help of wave theory of light, not the particle theory. Okay. Then I think you may heard about Isaac Newton's corpuscular theory of light. See, this corpuscular theory of light could not explain the interference or diffraction phenomena. So Christian Huygens, he proposes his wave theory of light. So this wave theory of light can explain the interference and diffraction phenomena. So up to that time, or during that time, light is considered as a wave. Okay, but uh, by the discovery of this photoelectric effect and Compton effect, again this light is a particle. Okay, then I think you may heard about the Davison-Germer experiment. See, Davison-Germer experiment actually demonstrate the wave nature of particle. Okay, photoelectric effect, particle nature of wave, and Davison-Germer experiment, wave nature of particle. Okay, so that's a problem. So we know that particle like electron or proton and neutron, they have wave-like properties. Okay, so particles like electron, proton, and neutrons, they have wave-like properties. You may heard about that Davidson Germer Thomson experiment. See, the incoming one is an electron, but we are getting as an interference or diffraction phenomenon, not interference, diffraction phenomenon. Okay, so which means that this electron exhibit a wave-like property. Okay, then we know that wave is a delocalized one, or we can say spread in space. Wave is spread in space. That's the concept. And particle is localized in space. Okay, so wave is spread in space and particle is localized in space. In the case of photon, if we can consider this photon as a particle or we can consider this photon as a wave. Okay, but the problem is the properties are entirely different, or we can say they are two extremes. So this Bohr complementarity principle, which states that wave and particle aspects of matter are complementary. See, wave and particle aspect of matter are complementary, both equally essential for full description of physical quantity. See, Bohr's complementarity principle, which states that wave and particle aspects of matter that are complementary, which means that both equally essential for the full description of a physical entity, which is essential for the full description of a physical entity. Now we are moving to the another topic called wave function. So what is called wave function? But we know that what is a function. For example, many times we may repeat f of x is equal to sin x, or f of x is equal to cos x, or f of x is equal to e raised to I k x, or e raised to x, or sin x plus cos x. Okay, it's a function. F of x means it's a function of x. Suppose it's a function of x and y, we may write f of x and comma y. If it is in three dimensions, we can say f of x, y, z. If it's dependent on time, then we can say f of x, y, z and time t. Okay, that's what we call function. So wave function means it's a representation or mathematical representation. So before discussing the wave function, uh, uh, I would like to tell you something about the matter wave. Okay, we will discuss that matter wave. Before that, our traditional understanding of particle is it is localized. Which localized means it has definite position, momentum, etc. It's confined to space. For example, see this is a pencil. It's a pencil. It has definite position and momentum. Suppose it's moving at a particular time. It has a definite position and momentum. Okay, so it occupies space with respect to some coordinate. So this pencil is placed x at a distance of x from this point y axis, and this axis we can locate. So particle is localized and it has definite position and momentum and confined in space. But coming to the wave wave it is delocalized, or we can say spread in space. Wave is always moving, which means that wave is spread in space. So how can we associate these two? Because as per the Bohr complementarity principle, or we can say the outcome of photoelectric effect and interference. So these are the two extreme entities or these extreme properties. How can we associate wave nature to a particle? How can we associate wave nature to a particle? Because the question is, the reason for this question is particle nature and wave nature, they are two extremes and that represent a single entity. How can we associate wave nature to a particle? Because particle is localized, wave is spread in space. So, or what could represent both wave and particle? See, there's a one main problem. So, particle is moving, wave is associated with that as per the de Broglie concept. How can we associate wave nature to a particle, or how can we represent wave nature and particle nature to a with a single entity or a single function? So in this situation, So we need to find a description of a particle which is consistent with our notion of both particle and wave. So what we need is, suppose this is a particle, we find a description in which it possesses both particle nature and wave nature. Okay, so as for that, what we need is we fit the wave description to that, and also localized in space. So it is something like a localized wave, we can say. It's something like a localized wave. So localized means the particle, wave is means spread in space. So we can say it's a localized wave. And how can we construct this localized wave? This is we can say, see this animation, you can find some wave is moving, which means that the particle is moving, and this moving wave, or that packet is called wave packet or matter wave, that we will discuss later. See, you can find, for explaining the wave packet, or representing the both wave nature and particle nature to a single entity. Before explaining that, I would like to tell you, see, there's a green wave, you can find a green wave, and there's a blue wave. If we add together, we will get the red wave, which means that the superposition of two waves gives another wave. Okay, so as I told you, uh, particle nature is there, wave nature is there. We need to combine these two, particle nature and wave nature, to a single entity. This is done by making making an assumption that this one is a localized wave. Okay, and this localized wave is called wave packet. Okay, this is nothing other than the wave packet, which means that the particle is moving, which means the wave packet is moving. The particle is moving means the wave packet is moving. Okay, so how can we construct this wave packet? We can construct the wave packet by the superposition of waves, superposition of different wavelengths to make a packet. For example, you see, this is a one wave, this is another wave having slightly different in wavelength. So these two waves undergo some sort of interference, constructive or destructive interference. So we will get a wave like this. And actually, this one is the wave packet, and the particle is moving means this wave packet is moving. Okay, once again, I would like to repeat the wave function, the particle which is localized, wave is spread in space. So how can we associate these two entities or these two properties to a single entity or single thing? Okay, and this can be done by localized wave. We can say in simple words, this can be done by localized wave. This localized wave is called wave packet, and this wave packet is formed by adding several waves, or simple words we can say superposition of superposition of waves having slightly different wavelength. Okay, and this one is called wave packet. Okay, so the particle is moving, the wave packet is moving. For example, the electron is moving, the wave packet is moving. How can we construct a wave packet? Wave packet consists of, please listen, wave packet consists of group of waves having slightly different in wavelength. The wave packet consists of group of waves having slightly different wavelength. Group of wave means it consists of, for example, 10 number of waves, and each waves have slightly different wavelength. Okay, and it undergoes slightly different wavelength means there's a possibility of phase shift. Okay, so what happens is these phases and amplitudes of the wave packets are such that they undergo constructive interference only over a small region. See, this region there's a constructive interference. After that, destructive interference. For example, I can say these regions are constructive interference, and this one is destructive. This is constructive, this is destructive. So the wave particle, sorry, the wave packet is moving, the particle is moving, the wave packet is moving. Wave packet is formed by superposition of different waves having slightly different wavelength, which undergoes constructive interference where the particle is likely to be found, which means that particle can be somewhere within this wave packet. We don't know where exactly it is. Okay, so outside the region, it undergoes destructive interference, which means that the particle is not there. So the particle is moving means the wave packet is moving. We don't know actually where the particle is located within this wave packet. Okay, so and such a wave packet, see, such a wave packet moves with its own velocity, which is called group velocity, that is called Vg. So wave packet is formed by constructive interference, or we can say a wave packet consists of group of waves having slightly different wavelengths, which undergoes constructive interference where the particle is likely to be found. Outside the region, particle is not found. And this wave packet moves with a velocity called group velocity, that is the velocity of wave packet, group velocity Vg, and individual waves can move with its own velocity, that is called the phase velocity, that we will discuss later. Okay, so wave packet, which consists of group of waves having slightly different in wavelength, which undergoes constructive interference where the particle is likely to be found, and destructive interference where the particle is not found. And this wave packet moves with a velocity called group velocity, and velocity of the individual wave is called the phase velocity. I think the concept of wave packet is clear. Okay, so the necessity of the wave packet is, so uh, we have both particle nature and wave nature. We need to associate, or we need to represent the wave and particle nature to a single unit. So that is nothing other than the wave packet. This wave packet is formed by superposition of different waves. From where we get the different wavelengths? As per the de Broglie concept, we know that lambda is equal to h by p. Okay, so this lambda is equal to h by p, then we will get a one wavelength. As per the Ansaldo principle, there is a possibility of the momentum is not accurate. There are a lot of wavelengths, and these waves add up to form a wave packet. Now we are in a position to describe wave function. See, for example, if there is a straight line, we can write y is equal to mx plus c. Suppose this is a straight line, we can write this straight line, this is equal to y is equal to mx plus c, or y of x is equal to mx plus c, where m is the slope and c is the y-intercept. This equation represents a straight line, y is equal to mx. Just like a function that represents the quantum state of a particle, that's called the wave function. For example, see, in this straight line equation, y is equal to mx plus c, from this equation you can easily find what is the slope, what is the y-intercept. Okay, isn't it? So from this equation itself, you can easily find what is the slope of this straight line, what is the what called the y, what is the y-intercept. Okay, similarly, wave function that describes the quantum state of the particle. Quantum state means what is energy, what is the position, what is the momentum in all direction. So we can say wave function is a probability amplitude in quantum mechanics. Okay, that I will discuss later what do you mean by the probability. Okay, so wave function is a probability amplitude in quantum mechanics describing the quantum state of a particle. Mathematically, it's a function from space. Please listen. It's a function from space that maps all possible state of a particle or system into a complex number. It's a function. Function means f of x. For example, f of x is equal to sin x, which means that it's just like a sine wave. F of x is a cos x, just like that. E raised to ikx, it represents a plane wave. So wave function is a function. It's a function from space that maps all possible state of particle. Or in simple words, we can say the law of quantum mechanics describe how the wave function evolve over time. The law of quantum mechanics describe how the wave function evolve over time. Okay, maybe in the coming sessions we may get some idea about the importance of this wave function. Okay, so wave function is very important in quantum mechanics. Actually, the main problem of quantum mechanics is to find the wave function, because wave function is a function from space that maps all possible state of a system in a complex number. For example, this is for an electron. If you find the wave function of this electron, you may get all the information about the electron, which means its position, momentum, energy, etc. Okay, so the law of quantum mechanics describe how the wave function evolve over time. Or another definition of wave function is the quantity whose variations make up the matter waves are called wave function. So suppose this is a matter wave, this is a matter wave which is moving, and psi of rt, psi represents the wave function. Psi of rt means it's a function of r. R means x, y, z. Okay, and t is the time. The quantity whose variations make up the matter wave is called wave function. Or we can say, to describe the matter wave associated with the particle in motion, one requires a quantity which varies in space and time. To describe the matter wave associated with a particle in motion, suppose this is a particle which is moving. To describe the matter wave associated with a particle in motion, one requires a quantity which varies in space and time. That is called the wave function, that is psi of rt. Okay, and this variable quantity called the wave function, it must be large in the region where the particle is likely to be formed. See, the value of this wave function is large in this region and it is less outside the region. Okay, so I would like to repeat once again what is wave function. So wave function is a probability amplitude in quantum mechanics, describe the quantum state of particle. Or we can say wave function is just like I told you your Aadhaar card, which describes almost everything about you, or your identity tag, your name, house name, from where you are coming, phone number, blood group, address, everything, which course you are studying. Just like uh, uh, wave function for an electron means it describes all the information about the electron. And the law of quantum mechanics describe how the wave function evolves over time. Okay, so and this parameter is a function which varies with time, space and time. Wave function is a function which varies with the space and time, which describes the quantum state of a particle. That's what we call the wave function. Okay, or we can say the wave function of a matter wave which is confined to small region of space named as the wave packet. See, this is the wave packet. Wave function of the matter wave which is confined to small region of space is named as wave packet. See, the particle is confined to this small region, and this region is called the wave packet. Okay, and there are some properties of this wave function. It can interfere with itself so that it can account the result of diffraction experiment. So it can interfere, which means that superposition principle. It obeys superposition principle. This wave function obeys the superposition principle. That is, it can interfere with itself so that it can account for the result of diffraction experiment. And its value is large where the particle or photon is likely to be small elsewhere, which means that its value is large in this region, outside region it's small. It's clear? The value of psi is large in this region, outside the region it is small. And wave function is considered to describe the behavior of a single particle or photon. Wave function is considered to describe a single particle or photon. That's what we call the wave function. Now we are in a position to interpret the physical interpretation of matter wave or wave function. What is the physical interpretation of wave function? Okay, now we discuss what is wave function. It's a function from space. We can say in simple words, we can say it's a function from space that maps all possible state of a particle. That's what we call the wave function. Okay, matter wave means the superposition of waves having slightly different wavelength which undergoes constructive interference where the particle is likely to be found outside the region it is zero or small, very small. And this wave packet is moving with a velocity called the loop velocity. Okay, the mathematical representation of de Broglie wave or matter wave associated with the given particle is a wave function, or we can say in simple words, we can say mathematical representation. Mathematical representation means sin x, a sin x plus b cos x, or e raised to ikx, e raised to ikx minus omega t. These type of terms are called the mathematical representation or de Broglie wave. Okay. Now, we wish to answer the following questions. Where is exactly the particle is located within delta x? See, this is the region delta x, where it is actually located. We don't know. We know that the particle is somewhere within this region, but we don't know where it is exactly located. Okay, but we can say this is the probability distribution. At this region, the probability is maximum. This region, probability is minimum. Okay, so recall that in the case of conventional wave physics, field amplitude square proportional to intensity. Field amplitude square. For example, a sine omega t is square. Suppose E is equal to E0 sine omega t, where E0 is the amplitude, E is equal to E0 sine omega t, the intensity is equal to E square. Field amplitude square is proportional to intensity. Now, modulus of psi of xt, the whole square, modulus of square of the modulus of psi of xt, or the wave function, modulus of the wave function, then its square, what it really means. So the physical interpretation of wave function is given by Erwin Schrödinger. Erwin Schrödinger gave the physical interpretation of wave function in terms of charge density. Physical interpretation of wave function was proposed by Erwin Schrödinger, which is in terms of charge density. Remember, intensity is equal to modulus of square of the modulus of psi f, or amplitude square. Amplitude square gives the intensity. And Schrödinger, he interpreted the wave function in terms of charge density. Suppose, for example, if A is the amplitude of the electromagnetic wave. So the electromagnetic wave means there is an electric and magnetic field. This electric field component can be written as A sine omega t plus kx, like that. Okay, if A is the amplitude of the electromagnetic wave, then energy density is proportional to A square. If A is the amplitude of the electromagnetic wave, then energy density is equal to A square. The number of photons per unit volume is equal to A square divided by h nu. So A square is the energy density, then number density is equal to A square energy density divided by energy of one photon, that is h nu. If A is the amplitude of electromagnetic wave, then energy density is equal to A square, which means that the amplitude square. A is the amplitude of electromagnetic wave, energy density is equal to amplitude square, that is A square. Then that is energy density, then number density is equal to that energy density divided by one photon, that is A square by h nu. Now you can look at this equation, the number density or particle density, which is equal to A square divided by h nu, but h nu is an energy of single photon, that is constant. So we can say the number density is proportional to amplitude square. The number density is proportional to amplitude square. If psi is the amplitude of the matter wave, now coming to the charge term, if psi is the amplitude of the matter wave, then the particle density is proportional to psi square. Particle density is proportional to psi square. See, if psi is the amplitude, suppose if A is the amplitude, then particle density is A square. If psi is the amplitude, then the particle density is proportional to psi square. Okay. If Q is the charge, then the charge density, not the particle density, charge density is equal to Q times psi square. Since Q is a constant, charge of an electron or proton, whatever it is, a constant, hence the particle density is proportional to psi square. So, Erwin Schrödinger, he proposed the particle density which is equal to or which is proportional to psi square. So probability of x is equal to modulus of psi square, which is interpreted as the probability density of observing the material particle. That is the particle density as such. It's a particle density. Once again, I would like to repeat. Erwin Schrödinger, he gave the physical interpretation of wave function. What the psi of xt really mean? So what is the meaning of the psi of xt? So he explained this psi of xt in terms of charge density. He proved that this charge density is proportional to amplitude square. So charge density or particle density or charge density, whatever it is proportional to amplitude square. That is the physical interpretation of wave function. But the problem is this wave packet associated with each material particle dissipate in the course of time. See, the wave packet is which is dissipate in the course of time. For example, we know that for example in sine wave, its value is dissipating in the course of time. So we cannot say the particle density is like that. This is the case. No, we cannot say. So we can say only the probability term, the probability of finding the particle. So in this circumstance, Max Born, he proposed the probability interpretation of wave function. Max Born's most important contribution was that the absolute square of the wave function in Schrodinger equation was the measure of probability of finding the particle at a given location. Actually, it is not the particle density, that is the probability. Okay, and Born, he shared a Nobel Prize with Bethe in 1954. Max Born, he suggested that probability interpretation of wave, suggested the probability interpretation of wave function. According to this, psi star, psi is the wave function, psi star is its complex conjugate, represents the probability density. Erwin Schrödinger proposes the particle density or charge density. Max Born, he added one more term, that is probability density. It is not the particle density as such, because the wave function dissipate in the course of time. Okay, so according to Max Born's probability interpretation, psi star psi or psi star represent the probability density. Psi star represents the probability. Psi is the wave function, psi star is its complex conjugate. Psi star is its complex conjugate. So psi star is the probability. So Max Born interpreted the product of psi of xt and its complex conjugate as the position probability density. Psi star is the position probability density. For example, see this blue line which represents a wave function, and this black line which represents the probability density. From this graph you can find this shaded region. This one is the maximum probability, and this region is the white part. This is the minimum probability, and this black line represents modulus of psi star psi or psi star psi or modulus of psi square, and this blue line which represents the wave function psi of xt, and this one is the black one is psi star psi or modulus of psi square. Okay, so Erwin Schrödinger, he proposes the physical interpretation of wave function, which states that which gives an information about the particle density. But the problem is wave function is dissipate in the course of time, so we cannot say the particle density is like that. Is this one or like that. So in this situation, Max Born, he proposes the probability interpretation of wave function. Max Born interpreted the product of psi and its complex conjugate as the position probability density. Okay, so probability of for a particle to be found between the point A and B. Suppose this is the case, this is the wave function. The probability of finding the particle between A and B, that is P of A and B. Probability of finding the x in between A and B, that is equal to integral P of x dx, that is integral A to B modulus of psi square dx. Its value is given by the area under the curve. That is a probability density. See, this quantity psi modulus of psi square theta or psi star psi is then the probability of finding the system at a time interval time t in a small volume element theta. When the modulus of square of the modulus of psi of xt theta is integrated over entire space, one would get the total probability. Okay, for example, see if you are putting some particle or some yes, a small particle in this glass. What is the total probability if we integrate from this point to this point? The total probability should be 1. Okay, if we integrate from one point to this one, there's a value, but the total probability may not be 1. The particle can be found somewhere in between. Okay, so if we integrate from this entire space, if we consider the glass, suppose if we think out of box, then suppose it's a minus infinity plus infinity, the total probability is 1. Okay, so Max Born he suggested that integral minus infinity plus infinity modulus of square of the modulus of psi x t d top, which is equal to what? The total probability is 1. Okay, so Max Born he proposes the probabilistic interpretation of wave function, which means that, or which states that was psi of xt as its complex conjugate, that product gives the probability position probability density. And if we integrate between any two value, for example in this case from here to here, you will get a number. And if we integrate from here to here, you will get the total probability. We know that the total probability is always 1. The probability cannot exceed 1 or below 0. Can be a value from 0 to 1. So the total probability is equal to 1. And these conditions of wave functions are: the wave function represent the particle must be normalizable. We will discuss later what you mean by normalization or normalization conditions. And the wave function must be single valued at each and every point. Each and every point the wave function should be a single valued. It cannot have multiple value point. Okay, which means that at a particular point the wave function represents something. For example, a particular point momentum value is constant. It's a single momentum value. It cannot have a two momentum value even in direction. It's not possible. And third condition is the absolute value at all points must be such that integral minus infinity plus infinity square of the modulus of psi of xt d tau which is equal to 1, which means that the total probability is equal to 1. Okay, so these are the three conditions of wave function. The wave function represents the particle must be normalizable, and the wave function must be single value. Its absolute value at all points must be such that integral minus infinity plus infinity psi of xt square of the modulus of psi of xt d tau which is equal to 1. Okay, now we are in a position to describe what we mean by group velocity and phase velocity. Group velocity and phase velocity. I already mentioned that there's a wave packet or matter wave or wave packet. Wave packet is formed by superposition of different waves having slightly different wavelength, which undergoes constructive interference where the particle is likely to be found and destructive interference where the particle is not found. And this wave packet moves with a velocity called group velocity. And there's a velocity called the phase velocity, which is the velocity of individual waves. That is velocity of individual, that we will discuss now, or that we will discuss now itself. See, we associated de Broglie wave with a moving body. So the previous class we explained what we mean by de Broglie wave, and that's an expression lambda is equal to h by p. That is the wave associated with a de Broglie wave. Now it is reasonable to expect that this wave will travel at the same velocity v as that of body, which means that this de Broglie wave velocity is and the particle velocity is these are same, but that is not the case. Once again I would like to repeat. See, suppose the particle is moving, there is a wave associated with the particle, that is called the de Broglie wave. Okay, and it is reasonable to expect that the particle velocity and this wave velocity both are same. And if we recall, or we call the de Broglie wave as Vp, de Broglie wave as Vp, And we may apply the usual formula to determine the value of Vp. Vp is equal to nu lambda, frequency into lambda. Okay, so frequency into lambda gives Vp, that is the de Broglie velocity of the de Broglie wave. And de Broglie wave, the lambda is equal to h by mv. From this expression, you can find lambda is equal to h by mv. And the nu is the frequency, then energy is equal to h nu. That we know. And nu is equal to E by h. Okay, frequency is equal to energy divided by h. And we know that E is equal to mc square. So from this expression, it's very clear that frequency is equal to mc square by h. The Broglie lambda is equal to h by mv, E is equal to h nu, and nu is equal to E by h, and we know that E is equal to mc square. So frequency nu is equal to mc square divided by h. And if we substitute the okay, so we get frequency is equal to mc square by h, and lambda is equal to h by mv. So Vp, see, Vp is equal to frequency into lambda, frequency is equal to mc square by h, lambda is equal to h by mv. So and this h will cancel, the m and the m will cancel. So what we get is c square by v. It's a very interesting result. C square by v. C is the velocity of light, v is the velocity of the particle. C is the velocity of light and v is the velocity. See, from this expression it is very clear that its value is always greater than c. So we cannot be same as that of c. So what happens is the de Broglie wave velocity or Vp should be greater than the velocity of light. That actually is not practically possible. So c square by v is the result, de Broglie wavelength Vp, and which is not practically possible because v is always less than c. See, please write this equation and you can find c is always or greater than v, or v is less than c, which means that this value is greater than the velocity of light. Okay, so de Broglie wave Vp is equal to nu lambda, or that which is equal to c square by v, which is not practically possible since the particle velocity cannot be equal or exceed the velocity of light. As per the special theory of relativity, we know that nothing can travel faster than light. Velocity of light is, that is the ultimate one. So the particle cannot even uh, move with the velocity, velocity with the velocity of light, or speed with the velocity of light. So the de Broglie wave velocity is always greater than the velocity of light. De Broglie wave velocity, please listen. The de Broglie wave velocity is the velocity or which is always greater than velocity of light. De Broglie velocity is always greater than the velocity of light. So therefore, v and Vp never equal for a moving body. So this particle velocity and phase velocity, they are never equal. The phase velocity is always or sometimes greater than the velocity of light, which is not practically possible. So in order to understand this unexpected result, we must look into the distinction between the phase velocity and the group velocity. So the angular frequency of the and the propagation constant of the de Broglie wave associated with the moving body of mass m0, rest mass m0, the moving m0 moving with the velocity v r. See, we know that omega is equal to 2 pi into frequency. That is 2 pi into, we can multiply with the h and divide by h. So what we get is 2 pi h nu by h, that is 2 pi into mc square by h. Okay, so because h nu is equal to E, that is equal to mc square, 2 pi into mc square by h. And we know that for relativistic expression for the mass, m is equal to m0 divided by square root of 1 minus v square by c square. This is the relativistic expression for the mass. Or we can say the variation of mass with velocity, where m0 is the rest mass, v is the mass when it is in motion. So if we substitute the value of m here, so what we get is 2 pi into m0 c square divided by h into square root of 1 minus v square by c square. So omega is equal to 2 pi into m0 c square divided by h into square root of 1 minus v square by c square. Okay. And the propagation constant k is equal to 2 pi by lambda. And we know that lambda is equal to h by p or h by mv. So what we get is 2 pi mv by h. Therefore k is equal to 2 pi into m. Instead of m, we need to write m0 divided by square root of 1 minus v square by c square. Okay, so what we get is k is equal to 2 pi m0 v divided by h into square root of 1 minus v square by c square. Okay, so both omega and k are functions of velocity. See, this omega and this k are functions of velocity v. So the phase velocity is equal to omega by k, and the group velocity is equal to d omega by dk or de by dp. Okay, so de Broglie wave associated with the moving body travels with the same velocity of the as the body. De Broglie wave associated with the moving body travels with the same velocity as the body. The wave or phase velocity Vp of the de Broglie wave evidently has no physical significance. This phase velocity or de Broglie wave velocity, which is having which does not have any physical significance, because the motion of the wave group, not the motion of the individual wave, makes up the group corresponds to the motion of the body, which means that group velocity is actually represents the motion of the body. Group velocity represents the motion of the particle, not the phase velocity. Phase velocity represents the velocity of individual waves. That individual waves, or group of that individual waves, group of waves that creates the wave packet. Sorry, that creates the wave packet. So wave velocity or phase velocity Vp of the de Broglie waves evidently has no physical or simple physical significance, because the motion of the wave group, not the motion of the individual waves, that makes up the group corresponds to the motion of the body. Okay, so now we can define what is group velocity and phase velocity. Group velocity is the velocity at which the overall shape of the wave moves. Group velocity is the velocity of group of waves. Group velocity is the velocity of group of waves, or the envelope moves. Wave phase velocity or wave velocity, both are same. Wave velocity or phase velocity, and that is nothing other than the velocity of individual phases of the wave. Phase velocity Vp of a monochromatic wave, monochromatic means single wavelength wave, is the velocity with which definite phase of the wave, such as its crest or trough, propagated in a medium. So wave velocity or phase velocity is the velocity of phase of individual waves, that is Vp, which is equal to omega by k. And in group velocity is it is possible to form a concentrated wave packet by taking sum of large number of plane waves with slightly different wavelengths and frequency. That is matter wave or wave packet itself. So wave packet is a group of waves, and this wave packet is moving with a velocity. That velocity is called the group velocity. Okay, and this observed velocity is the velocity with which the maximum amplitude of the group of waves advances in the medium, and this is called the group velocity. Okay, so group velocity is the velocity with which energy in the group is transmitted. So in simple words, we can say group velocity is the velocity of group of waves, or matter wave, or wave packet, or we can say the particle. And the phase velocity or wave velocity, that is the velocity of phases of the individual phases of the wave. Okay, I think it is very clear. Okay, so phase velocity is the velocity of individual phases of the wave. So from this figure, you can easily animation you can easily find. See, this black dot moves with the group velocity. See, the envelope is moving. See, black dot, this envelope is moving, and this velocity is called group velocity. And see, from this expression you can find this red one, the phases are moving. See, these phases are moving. That is the phase velocity or wave velocity. Okay, shall I repeat once again? See, the red one is the group of waves in the envelope is moving. The red one is the phases of individual waves are moving. That is the phase velocity. red dot moves at a phase velocity and black one is that moves with a group velocity. Now we are in a position to explain what is uncertainty principle. Uncertainty principle. Even from your plus 2 class, you may heard about the Heisenberg uncertainty principle. That is one of the pillar stone in quantum mechanics. Uncertainty principle proposed by Werner Heisenberg in 1927, for which he awarded the Nobel Prize in Physics in 1932. See, according to classical physics, a moving particle has definite momentum and it occupies definite position in space, and it is possible to determine the position and momentum accurately. Okay, for example, see, one car is moving at a particular time. We can calculate its position. At a particular time, we can calculate its momentum. At particular time, we can calculate both position and momentum. Okay, so in classical mechanics, it is possible, but in quantum mechanics, the particle is described by wave packet. So classical physics, position and momentum of particle can be easily calculated simultaneously and precisely. But in quantum mechanics, the particle is moving means the wave packet is moving. We don't know where the particle is exactly located within this wave packet. I would like to repeat once again. The particle is moving means the wave packet is moving. The particle is moving means wave packet is moving. And we don't know where the particle is exactly located, but we know that it is somewhere within this wave packet. Okay, it is somewhere within this wave packet. So the particle is moving means the wave packet is moving. So the particle is somewhere within this wave packet, and there is an uncertainty that is delta x. And this indicates that the position of the particle is uncertain within this limit. So particle may be here, maybe here, maybe here, like that. There's a lot of possibilities. So moreover, the wave packet has velocity spread also. So there is an uncertainty about the velocity. So it has a velocity spread or momentum spread. So there is an uncertainty in momentum. So uncertainty principle, if x coordinate of the position of the particle is known with an accuracy of delta x, if we can find the accuracy of position of this particle with an accuracy of delta x, then its momentum accuracy is of the order of h by delta x. Or in other words, we can say that there are it is impossible to measure two canonically conjugate variables simultaneously and precisely. We cannot measure simultaneously and precisely two canonically conjugate variables. Two canonically conjugate variables means like position, momentum, energy, time. See, position, momentum, delta x into delta p, energy delta E into delta t, and delta phi angular momentum into C. This is the angular momentum, delta L in angular momentum, phase angle delta phi. Okay, so the essence of this uncertainty principle is that more precisely the position is measured, the momentum accuracy may disturb or perturb. Okay, and this Heisenberg uncertainty principle is an important consequence of wave-particle duality of matter and radiation, and is inherent to the quantum description of nature. So uncertainty principle states that it is impossible to measure both position and momentum, energy and time, or angular momentum phase angle simultaneously and precisely. We cannot measure simultaneously and precisely. If we measure the position of the particle accurately, then its momentum value accuracy may disturb. If we exactly measure the position, then the accuracy of momentum is infinity. If we exactly measure the value of momentum, its position accuracy goes to infinity, which means that it is not accurate. Okay, so that's Heisenberg uncertainty principle. In terms of position and momentum, that is delta x into delta p is greater than or equal to, or we can say of the order of h gross. This h by 2 pi is called h gross. This h by 2 pi is called h gross. So delta x into delta px is equal to h by 2 pi, which is equal to h gross. So Now, uh, we can measure the position and moment of electron. Suppose there is an electron. Okay, how can we observe this electron? Then shooting a light into this electron after scattering, it goes back to the or reflected back to our eyes or some other measuring instrument through some other measuring instrument. Okay. Anyway, we shine a light into this electron and detect the reflected light. Okay. We need to shine a this electron and analyze the reflected light using microscope or something like that. Since it's an electron, first we shine an electron. Shine light on electron. First we shine light on electron, which means that some light has to fall on this electron. After reflection, it goes back to the our microscope. Okay, so minimum uncertainty in position is given by the wavelength of the light. So uncertainty in this is given by the wavelength of the light. Suppose this is an electron, its uncertainty is given by the wavelength of the electron. Okay, so suppose this is the wavelength. Suppose this is the wavelength, its accuracy is of the order of wavelength. Okay, well, in simple words, we can say the minimum accuracy is the wavelength, the dimension of the wavelength. The wavelength is shorter, which means that we can accurately measure the position of this electron. Suppose this is electron. Suppose this is the wavelength, very long wavelength. Sometimes it may not see this electron. Okay, suppose the wavelength is very small. Okay, so this light can detect this electron. So which means that the minimum uncertainty in position is given by the wavelength of the light. So to determine the position accurately, it is necessary to light with a shorter wavelength. Okay, its position we need to find the position uh, uh, wavelength of shorter wavelength, light of shorter wavelength. Shorter wavelength means higher frequency. Okay, so in order to measure the position of this electron, we need to use a shorter wavelength. Then only it will touch. Then only we can find the position of the electron accurately. So shorter wavelength means higher frequency. Higher frequency means higher energy. Okay. So uh, what happens is higher energy light falls on this electron, which means that this electron gets some energy from this light. In order to measure the position accurately, we need to use lower wavelength. Lower wavelength means higher frequency. Higher frequency means higher energy. This high energy impart a large kick on this electron. So this large kick always perturb the system. So that is the problem. So in order to determine the momentum accurately, first we measure the position accurately, then its momentum value disturbed. So in order to measure the momentum accurately, what we need is we need to use a very long wavelength. Okay, so in order to determine the momentum accurately, the electron must only be given a small kick. Okay, then only we will get the momentum accurately. Small kick means small energy wave. Small energy wave means small frequency wave. Small frequency wave means larger wavelength. So that's a problem. So the use of light with a short wavelength, we can accurately measure the position but not momentum. Okay, use of light with a short wavelength, we can measure the position accurately. Use of light with the long wavelength, we can measure the momentum accurately, but the other parameter. Okay, so use of light with a short wavelength, accurate measurement of position is possible, but not momentum. Use of light with a long wavelength, accurate measurement of momentum is possible, not position. So the act of measurement influences the electron. It gives a kick and it is no longer where it was. That is the essence of uncertainty principle. The act of measurement influence the electron. Okay, so act of measurement always influence the electron, and that gives it a kick and it is no longer where it was. Oh, which means that measurement always perturb the system. Okay, measurement always perturb the system. For example, if you are conducting an exam, that always perturb the system. Perturb the system means perturb you even after measurement. Okay, after measurement, either you may be happy or sad, depending upon the examination, the result of examination. So Planck's constant is so small that, say, another important thing is Planck's constant is so small that uncertainties implied by the principle are too small to be observed. They are only significant in the domain of microscopic system. Why it is not applicable in macroscopic system? For example, this car is moving. What is the uncertainty? Suppose the car is moving. What about its uncertainty value? Its uncertainty value is very small. It is not. It is insignificant. For example, see, for macroscopic system, the position is always represented in terms of meter or something like that. That 1 meter plus 10 raised to minus 34 meter. It is insignificant. Okay, for macroscopic system it is insignificant. For microscopic system it is significant. So Planck's constant is very small, so its effect is negligible in the case of macroscopic system, but significant in the domain of microscopic system. So we discussed it. So far we discussed it. Bohr correspondence principle, Bohr complementarity principle, wave function, wave packet, physical and probabilistic interpretation of wave function, then group velocity and phase velocity, then uncertainty principle. Okay, thank you very much.